Hello everyone, welcomes to all in our lecture series on optics, that is your B.sc Physics Honors syllabus second semester. This is your core 4 paper. Okay, in this video we are going to discuss Fresnel's diffraction. This is your part 1 video. In this part 1 video we are going to discuss introduction about diffraction, Fresnel's assumptions, Fresnel's half period zone. In our next video or part 2 video, we are going to discuss coronospiral or Euler spiral and Fresnel's integrals. Let's start from introduction about diffraction. In your day-to-day life, may you have been observed that light when passes through the trees, it looks like straight line path like this. If we are going to consider a source of light, when it will pass through this slit, it will move like straight line path. That means if we are going to put a opaque over here along this path, then it will be obstructed. The full light will be obstructed, which is so-called rectilinear propagation of light. But if we are going to consider the slit width is very small, approximately micrometer range, then the light is not going to propagate only straight line, also propagate along this direction and along this direction by diffracted through this edge. Okay, and we are going to get the corresponding diffraction patterns like this: bright dark fringes we can observe on the screen, and this is the so-called the diffraction, or we can say light bends at the edge of the slit, and this is nothing but called as your diffraction pattern. Okay, this diffraction pattern can be explained by wave nature of light, which is done by Fresnel. Okay, so before we have to discuss Fresnel's diffraction, first we have to go through the Huygens wave theory, because Fresnel's diffraction explained with the help of Huygens wave theory. Okay, first we have to discuss Huygens wave theory. So for that, consider an isolated source. From this isolated source, the light will be propagated, and this is also called as your primary source. The light will be propagated from this primary source along all the directions like this. Now we are going to consider a imaginary circle over this primary source like this. So for the 2D, this is a circle, and for 3D, you just imagine this is a sphere. On each and every point of this circle, or in case of 3D sphere, at each and every point phase is same. That means suppose light is traveling along this direction, here what will be the phase? Here the phase will be same, here the phase will be same. That also you can say the phase difference between the 2 points will be 0. So here this is the imaginary circle we have been considered around the primary source, which is called as your primary wave front. Okay, according to Huygens wave theory, the primary wave front again divided into large number of secondary sources, or you can say according to Huygens wave theory, each and every point of this primary wave front is to be considered as the secondary sources. This is our primary sources, but each and every point on this primary wave front will be considered as the secondary sources. So these are our secondary sources. These are the secondary sources. So consider any one of the secondary source. From this source also the wave will be travel, or the light will be travel in all the ways, in all the directions. So this small circle will be called as the primary wavefront for this source. Okay, but this this wavefront this wavefront will be called as the secondary wavefront for the primary source. If this is your secondary source, this will be the primary wavefront for this source, but this wavefront will be considered as the secondary wavefront for this primary source. So if I will join all the points on the circumference of small circles like this, then this resultant wavefront, the blue color circular curve you just watch, this will be called as your secondary wavefront for this primary source. Okay, likewise we can consider each and every point of this wavefront will be considered as the tertiary sources for this primary source. Okay, so this will be the your tertiary source for this primary source. Okay, so as this will be the source, then from this source also the wavefronts will be propagated in all the directions. So this circle will be called as the primary wavefront of this tertiary source, but this wavefront will be called as your tertiary wavefront of this primary source. Likewise we can consider further forward and forward wavefronts. Okay, so here you just consider, if this is your primary source, this one is your primary wavefront, each and every point on the primary wavefront will be considered as the secondary sources, and this is your secondary wavefront. In this way the wavefronts will be traveled along all the directions from the primary source. This is your Huygens wave theory. This theory has been considered by Fresnel, and Fresnel given the diffraction theory by considering this wave theory, Huygens wave theory. Okay, and these are your circular wavefronts, and likewise we can get cylindrical wavefronts for the linear sources. This is one source. If we are going to consider linear source, then we can get cylindrical wavefront, and likewise also we can get the plane wavefront. Okay, so here we have been concluded that according to this Huygens theory, wavefronts are propagating in all the directions from a primary source. Now we are going to understand that how this Huygens wave theory is useful to understand the diffraction in our next slide. So here we are going to understand that how Huygens wave theory is useful to understand the diffraction, because the Fresnel assumed this theory, Huygens wave theory, to explain the diffraction. So for that, to understand how Huygens theory is useful to understand the diffraction, we consider the two situations. Here one slit and another one is your object or opaque. Here you can see, as we discussed in our previous slide, that from the primary source wavefronts are traveling in all the directions. We consider along this direction. Here you can see that wavefront is striked on this slit, and here wavefront striked on this object. So for this case, one can expect that if light is moving along the straight line path, then as this is the slit width, this much is your slit width, this one is your slit width, so light will be travel only the straight line path. One can expect that light will be travel along this direction, and it will illuminate only this portion of the screen, and this portion light not to be illuminated, because here somebody is considered that light is travels along straight line path. Okay, so here this region and this region is called as your shadow region. Shadow region for this case. Okay, likewise for this case one can expect that here this is the opaque or object is there. So if light is travels along straight line path, so this much portion of the screen not to be illuminated by the light, because this is the object is here, so light will travel above this and below this. So illuminated regions for this case is this one and this one. Okay, so this portion will be called as is your shadow region for this case. Shadow region. Okay, shadow region for this case. This is the shadow region for this case, and for this case this portion and this portion is the shadow region. But how the light travels to these shadow regions? Here we are going to understand. Carefully you have to watch. Consider this wave front is striked on this slit. So this much portion of your wave front is travels through this slit, and this portion is obstructed by this opaque region. So this much portion of the wavefront moved to the next side of this slit, suppose this one. And as we discussed in our previous slide that each and every point of the wavefront, each and every point of the wavefront will be act as the secondary sources. So these are the secondary sources from which wavefront is going to again propagate from towards all the directions. Okay, so consider this wavefront. If this wavefront will be propagating all the directions, so obviously this wavefront will be propagated along this direction and illuminate this region. This is the shadow region. Consider this wavefront. This wavefront will be propagated in all the direction, then it will be propagated towards the shadow region and will be illuminate this region. So here, according to Huygens wave theory, the wavefronts will be travel in all the directions, due to which the shadow regions also will be illuminated. Okay, likewise for this case you can see that suppose this much portion of the wavefront is going to be obstructed, this much portion. Okay, now this portion and this portion is going to be moved in the next side of your object. Consider this one, this wavefront. Here this wavefront means each and every point will be act as your secondary source. From this source light will travel in all the direction. For this source, from this source light will travel along all the directions. So if it is so, this wavefront also travels to this region, okay. Now you just consider this wavefront. Wavefront means each and every point will be act as a secondary source. You just consider this is, if this is a source, then from this source the wavefronts will be travel in all the direction. From this wave secondary source also wavefronts will be travel in all the directions. Okay, likewise from this source also wavefronts will be travel on the direction, all the directions. Consider this wavefront. When this wavefront is going to propagate in all the direction, also this wavefront will be propagate towards this region, which is the so-called shadow region for this case. So here we found that according to Huygens wave theory, the light is travels not only the illuminated regions but also travels the shadow region. Here for this case, this is the illuminated region and this is the shadow region. According to Huygens wave theory, light also illuminate this region or going to be moved towards this region and this region, the so-called shadow region. For this case, this region is your shadow region. So according to this theory, this area or this region also illuminated, due to which we can get the fringe. See, if we are going to get the fringe at this point and this point, then without this shadow region for this case. And for this shadow region, if we are going to get some fringes like this, then without any interference of the light, the fringes not to be appear. So in the shadow region, for this case, this region also we found the fringes. That means here light also falls or interferes with each other. For this case, in the shadow region also we found the fringe patterns. That means here also interference happens. That means due to these secondary sources, light will be travel to this shadow region, due to which we can get this type of fringes. Okay, now we are going to go for the Fresnel's assumption. Okay, so these are the four assumptions. The first one is the wavefront will be divided into large number of strips or zones called Fresnel's zones or Fresnel's half period zones of small area, and resultant effect at any point on the screen will depend on the combined effect of all zones from which light is passed through. So here this is your wavefront, and this wavefront is going to be divided into large number of zones. This is your, this center bright one is your first zone, then second zone, then third, then fourth, like that. So this is the first half period zone, second, third, fourth, fifth, sixth, light zones or strips, which are called as your Fresnel's zones or half period zones. That means a wavefront will be divided into large number of strips or zones. How it will be constructed, that we are going to discuss in our next slide. First we have to discuss the assumptions. So large number of zones, the resultant effect at any point on the screen, that may be O, that may be P, that may be any point on the screen, will be depend on the combined effect of all zones, that we have to consider. Whenever we are going to calculate the effect or resultant intensity at a point on the screen, then we have to consider all the zones, okay, through which light will be passed. Okay, next, second point is your, the effect at point due to any particular zone will depend on the distance of the point from the zone. So we are going to consider the point P is our observed point where we are trying to find out the effect. So for according to second assumption, the effect at point P, suppose from any zone, suppose we have to consider the center one, the distance from the zone to the point P is also to be considered. Suppose here you are going to consider the point P and point O from the center or from the first half period zone. It is different from this is C is the center of the first half period zone. From the C to O and C to P, both distances are different. So only for that, here the second assumption is written as the effect at any point due to any particular zone, suppose this one, will depends on the distance of the point from the zone. From the point to the zone, what will the distance, that will be considered. The third one is the effect or the intensity at point P or any point P on the screen also depends on the obliquity factor of the point with reference to the zone under consideration. Suppose this is the point, and this point where we want to calculate the intensity or effect. For that also we have to consider the obliquity factor of the point with reference to the considered zone. Suppose we are considering the first zone, what will the obliquity factor of the point P correspond to this zone? Suppose we are considering the second zone, what will be the obliquity factor of the point P correspond to the second zone also to be considered. Okay, the fourth one is your effect or the intensity at point proportional to the obliquity factor. And here the obliquity factor is considered as 1 plus cos theta. Here we are going to understand that how the obliquity factor is proportional to the intensity or effect on the screen at any point. Okay, first we have to consider the point P. The point P and the first half period zone, this one, white patch, white strip, you can say the center one. From the this first half period zone or first Fresnel's zone, the distance is your CO. Okay, and the angle between CO from the center, how much will be 0. So for CO, along CO, if we are going to consider along CO, this theta will be 0 and the obliquity factor is 1 plus cos theta. Cos 0 is 1, so 2, and the effect or the intensity will be maximum that we are going to consider. Okay, now we are going to consider another point. Suppose T over here, and the angle from this center or from this line to this point is this one. Suppose this angle is your 90 degrees. This T is at top of the screen, and suppose this angle is your 90 degree. So what will the obliquity factor for this point with respect to first half period zone? Here theta we considered as 90 degree and cos 90 will be 0, and along CT for this point P correspond to this zone, the obliquity factor will be how much? Will be 1. If 1, then it is represents the intensity is to be decreased. You just imagine the light is travels through this zone, through this first half period zone. So much more the intensity will be maximum at O, obviously, along the straight line path. If we are going to trying to find out the intensity at a point T through this hole, then it will be decreased, obviously. So light will be travel along the straight line path, maximum intensity we can found at O, and if we are going to go on the top side or bottom side of the screen, then the intensity will be gradually decreases, which is indirectly we can say represented by obliquity factor. Okay, so along CT, the intensity decrease as compared with CO. Likewise, if we are going to consider theta is 180, 180 means this one, 180 means this one. So here we considering that the light is traveling along backward. It is not possible because the wavefront is traveling along this way, and we are trying to observe the diffraction pattern this side, right side of this slit, but left side there is no observations. So if we are consider the light is traveling along this way, there is no screen in your left side, so hence we could not consider along CS path. Okay, so here as our screen is your right side of this slit, and theta for the theta 180 degree, that means along CS the obliquity factor is 0, because cos 180 is your -1 plus 1 will be 0. It is suggested that secondary wavefront eliminated. That means secondary wavefront which is passed through this light is eliminated. It is not present along this way. So these are the 4 assumptions by Fresnel for explaining the diffraction. Okay, next we are going to go for the Fresnel's zone or Fresnel's half period zone, how it will be constructed. Okay, as we discussed in our previous slide, that when the wavefront is going to be strike on this on a slit, then it is passed through, and this much portion and this much portion is going to be blocked. Right, now here how we are going to construct the Fresnel's half period zone. Suppose we are going to consider along straight line path, this is the point O on the screen, and this is the center we have been considered, and we are going to construct the imaginary spheres for 2D circle, for 3D imaginary spheres like this, which will cuts or intersects with the spherical wavefront. Okay, so here we consider one circle which cuts or intersect the spherical wavefront at here. Next we considered another circle which is cuts the wavefront at here and here. Okay, next another imaginary circle we have been considered which cuts at point here and here of this wavefront. So these are the imaginary sphere we have been considered which cuts the wavefront at here and here and here. So see, the first circle whatever we considered, this circle is intersects or cuts the wavefronts at here. So what is the portion it cuts? That portion is called as your first half period zone. This one. So you just consider the the first circle it cuts the wavefront. Here you can easily understand. So this one will be your first half period zone. The second sphere or the circle cuts the wavefront here and here. In between that, whatever the area we found for the wavefront, that will be called as your second half period zone. Okay. Then third circle we considered which is cuts the spherical wavefront at here and here. So in between that, so see, this portion and this portion will be a one type of circle. See, this is the wavefront, is looks like a arc, but you just consider in case of 3D it will be a portion of the sphere. If it is a portion of the sphere and we consider another sphere is going to be intersect with this wavefront, then it will cuts here and here, and in between this portion we are going to get another zone that will be called as your third half period zone or Fresnel's third half period zone. So this one is your this portion. This is called the first half period zone. This portion is nothing but this one. This portion, this much portion will be called as your second half period zone. This white patch is nothing but this one. This portion will be called as your third half period zone. Likewise, we can consider other circles or spheres for constructing the Fresnel's half period zones. Okay, these dark and white annular zones are called Fresnel's half period zones. Next, we are going to consider the construction of half period zones or Fresnel's zones by considering a plane wavefront. So this was our spherical wavefront, and here we considered a plane wavefront. So when the plane wavefront is going to be strike with the slit, it will be passed through the slit, then this wavefront is going to be divided into large number of strips by considering the same procedure. That means we have to consider this point, the straight line path from the source, it will meet at O, and this point O will be considered as the center, and considering this point as center, we have to draw the imaginary spheres for the 3D or circles for 2D. It will be cuts to the wavefront, and we are going to get the half period zones. This is the first, second, third and fourth and so on half period zones. These are the imaginary spheres. Okay. Now here we constructed the Fresnel's half period zone. The center one is your first half period zone, then dark patch or dark strip is called as your second half period zone. This one is your third, fourth, fifth and so on. So here this is your center for all the zones, as these are the circular zones. So this is the center, and from the center we can calculate the radius. So this will be the first half period zone, second, third, fourth and so on. So from O to at the edge of this white strip or white annular zone at the edge, to the edge is called as your, you just consider this point is your M1. O to M1 is your radius of first half period zone. From O to end of the edge of the second half period zone, let this point is your M2 and this distance is your radius of second half period zone. Likewise, from O to this point at the end of the edge of the third strip or third white strip, you can say, this point, mark my pointer. Okay, this point, if we are going to consider M3, then from O to M3, here you can see this point will be considered as M3, this point is considered as M2, this one is your M1. So O to M3 is your third half period zone. Likewise, from end of the edge of the fourth zone, this is your fourth zone, fourth strip. Okay, at the end, suppose this point is your M4, this point, and from O to M4 the distance is called as your fourth half period zone. Likewise, suppose from O to this point, we are going to consider this point at the edge of the fifth strip, the distance from O to, suppose this point is called as your M5. So O to M5 is your radius of fifth half period zone. Likewise, sixth half period zone, this one is your sixth half period zone, O to M6. Likewise, from this to this point, if this one is your seventh, this is the seventh strip. So this, suppose this point is your M7. So this is your this distance is your radius of seventh half period zone. Similarly, if we are going to consider some arbitrary zone, then it will be called as your Mn and the so-called nth half period, radius of nth half period zone. Okay. Now, Fresnel assumed another important assumption that by considering Huygens principle, that the ray coming from each alternative zone have phase difference pi, corresponding path difference will be lambda by 2. Here you can see this is the first zone, this is the second zone, the ray coming from first zone to P along this path. Okay, and the ray coming from the second zone will be along this path. Okay, so both have the phase difference is pi. Phase difference is your pi. Likewise, considering fifth and sixth, also phase difference is your pi. Okay, so if phase difference is your pi, corresponding path difference will be obviously lambda by 2. We know that phase difference, we know that the phase difference is equal to 2 pi by lambda into path difference. Okay, path difference. So here phase difference is pi. So pi equal to 2 pi by lambda into path difference. So here lambda, pi got cancelled. So we can get the path difference equal to lambda by 2. Right. So this is the assumption, important assumption assumed by the Fresnel. So if it is so, then what is the distance traveled by this ray and this ray? So if this will be O to P is your B, then this length will be obviously B plus lambda by 2. Okay, because obviously this is the larger distance as compared with the OP. How much large? That will be lambda by 2. So B plus lambda by 2. Then for third half period zone, it will be B plus 2 lambda by 2. Okay, two consecutive rays have lambda by 2. So if I am compare this ray, this third one to OP, obviously it will be 2 lambda by 2. For from the fourth half period zone, it will be B plus 3 lambda by 2. Then for fifth, B plus 4 lambda by 2. For sixth one it will be b plus 5 lambda by 2, and for seventh one it will be b plus 6 lambda by 2. Okay, see here I considered, see this is the first half period zone. For the first half period zone, this is your OP, that is your B. For the second half period zone, here I consider from here, wherever the second half period zone starts. Here you can see the second half period zone starts from this point. Okay, the second half period zone starts from this point. Okay, from this point to this point. So I consider this one, the second one, from the starting of the second half period zone. Okay, for this one it is your b plus lambda by 2. Likewise this one, this, if we are going to consider this path, this is for fifth half period zone, because this is starts from uh, starting edge of your fifth half period zone. So this, for this one it will be here you can see b plus 4 lambda by 2. Okay, so likewise this will be n minus 1 lambda by 2. You just correct it. Uh, just correct it. This will be n minus 1 lambda by 2. N minus 1 lambda by 2 for nth half period zone. So for nth half period zone it will be b plus n minus 1 lambda by 2. Now we are going to consider what will be the intensity at point P by considering all the half period zones. Okay, for as we discussed that the path difference between the two rays, which is coming from the first ray, first half period zone and second half period zone, is lambda by 2. So the path covered by the light which is coming from this first half period zone is B, and the light coming from second half period zone is your B plus lambda by 2. Okay, so the path difference will be how much? That is your lambda by 2. Okay, now the corresponding phase difference is your pi. Here we consider that M1, M2, M3, M4, M5 and so on are the amplitude of vibration at point P due to first, second, third and so on half period zones. So here M1 is belongs to the amplitude of vibration due to first half period zone, M2 is the amplitude of vibration due to second half period zone and so on. So as phase difference is pi, suppose we consider that due to first half period zone the vibration along this direction and amplitude is your m1, and due to second half period zone the vibration will be this direction opposite to this one, because phase difference is pi. If the vibration due to first half period zone will be along this direction, as phase difference is pi, then the vibration due to second half period zone at point P will be opposite with first half period zone and amplitude is m2. Similarly, vibration due to third half period zone will be opposite to the second one along this direction. Likewise, for due to fourth half period zone, the amplitude will be this much, but it will be vibrate opposite to the third one along this direction. So if we are going to consider the resultant intensity or effect at point P, we have to add all the amplitudes. Okay, so the resultant amplitude at point P will be M1 minus M2 plus M3 minus M4 plus M5 minus M6 and so on, because the amplitudes, vibration of amplitudes of for the conjugative zones are opposite with each other. So M1 along this direction means M2 opposite direction due to phase difference pi, so they are going to subtract. M3 will be add up because M3 along same direction as first half your zone. Okay, in this way we can evaluate the resultant intensity at point P by considering all the zones. Now we are going to go for the Coronal spiral or Euler spiral, how it will be calculate, that we are going to discuss in our next class. In our next class also we are going to discuss about Fresnel's integral. Okay. So thank you so much for watching this video. Thank you.